let us look at what can be done in order to improve this model. So, we are looking at the bits and pieces of conversational modeling. We are not looking at every aspect of that. So, initially we showed that it is possible to do some kind of a conversational modeling using information retrieval system, right. And now we see that it is not enough to give you a good retrieval. So, what should be added as part of this? So, as we mentioned earlier, finding the accurate answer is important rather than giving a set of relevant documents. So, that is not what IR based models are providing, right. So, I need the span of tokens. So, there is no way I can go and then say that okay, from the 10th to 15th word pick up the answer and then give me the response. So, we do not have a mechanism that is evolved as part of the IR model. So, we need to bring in additional mechanism that should be able to go and then pick up those span of text and then respond positively to the user queries. So, let us look at some samples and then see what can be done in terms of breaking the query into various pieces in terms of hierarchy and type, and see if that could help us in terms of achieving the precise answers for the query. Let us take a look at some of the questions, right. So, what is RNN? So, we know that there is an abbreviation here. So, we can create a hierarchy called abbreviation, and then when what is asked, when what is the part of the question, we are expecting an expansion for that, right. When there is an abbreviation, we want the expansion for that. Where is the big temple in India located? So, where gives you the hierarchy called location. Okay, let us pick up what is a prism. So, we know this is a question and it is expecting a definition. So, it is expecting a description from you, and the description is in the form of a definition. Why is the sun yellow? Again, it is a description at the very high level. Since y is there, so we need to find the reason for why the sun is yellow. Okay. And then there is one numeric part, how far away is the moon. Okay. It is a numeric, and we need to look at the or rather classify the type as a distant. So, we can create a set of hierarchy based on the question, and then use the hierarchy to fine tune or create more finer details for each of the questions. So, now if you look at RNN, it is very well known that it is a recurrent neural network. It is an abbreviation for the recurrent neural network, and we just have to provide the expansion. And if you go to this question, what is a prism? It is expected at the very high level. At the very high level, this is a hierarchy, and we need to provide the definition. So, you can classify most questions in 6 major classes such as this, okay, like abbreviation, entity, description, human, location, numeric value, and so on. And then all these 6 major classes again can be classified into fine grained types. Okay. So, how do we learn this? So, that is the next question, right. So, now based on the information retrieval model, we only worried about the keywords part. Now, we are able to create some kind of a hierarchy and fine grained types. Can this help in terms of understanding the query better is what we want to find out. So, maybe you may want to look at this paper on learning question classifiers, where the details of all these hierarchy and types are well documented. Now, look at the feature space. We have words, that is what we used in the IR model. So, we can get the part of speech for each of the words. We can get chunks or 2 or more words joined together, and then named entities. We can have head chunks using the POS. For example, for the problem that is stated here, a trip to Cape Carnival, Florida takes 10 hours, the distance is 816 kilometers, calculate the average speed. Okay. So, now we need to find the answer to this question. So, when you take it through the POS, you will see that there is a determiner, and then trip is a noun, and then there is a preposition here that is coded as ADP. We have a noun, and then there is a punctuation, noun, and so on, right. So, we are able to get the part of speech for all of this in this fashion, and then you have a question at the end. So, based on the keywords that you have created, in this case it is not possible to identify question if you do not have a set of keyword defined for it. In the case of kinematics, there are about 8 or 10 different verbs that you can use to distinguish the sentence from the normal statement from a question. Okay. So, in this case you will see that calculate is part of the question or tagged as part of that, and then we have average speed. So, this is what I am talking about as chunk here. So, in this case the chunk is coming from the adjective and the noun here. So, this is your chunk, and then if you look at that chunk, you know that, and this is what you want to find out. Calculate is the keyword in the question, and then this chunk will tell you what you want to find out. Okay. And this is what we are talking about here. And then semantically related words that often occur with a specific question class: how far, how high, how long, right. So, in this case you know that it is talking about, this is talking about distance, again this is distance, and this is time in most of the cases in the kinematics problems. Okay. So, now we can expand our feature space with all the other new features. It is not going to be just about words alone. And then in the question typology rules, we can start creating simple rules such as this: if the question starts with who or the question starts with whom, then the top hierarchy is human and the class is person. So, in this fashion you can create or rather you can classify the questions in this fashion. What is going to be the top hierarchy, what is going to be the type. If a query contains which or what, then the head noun phrase determines the class as for what X questions. So, in this case what, and then here you have the noun phrase, right. So, this determines what is to be extracted. Okay, that is what is being said in this. Okay, again you can use the decision rules such as these. and then for all the questions that you have, you can find the course class or the hierarchy and the find types. So, the idea here is to find the top hierarchy and the fine grained types. Okay, so, if you read through the paper, you will be able to understand the algorithm described on the right side very well. So, here what they try to do is, instead of creating only one hierarchy value for each of the word, they try to get more than one. So, they have the size of 5. There could be wrong classification if you just pick up one of the values for the hierarchy value. So, they try to provide 5 different hierarchy values based on the score that they compute, and then based on the query and the response that you are looking at, they use all of those to find out which one really match really well with the post or response. So, that is why they are keeping the hierarchy values to 5. I mean, there will be, for each word there will be 5 hierarchy values that are available. So, in the same fashion, even the fine grained values will be chosen. For each one of the word, there will be at least fine grained types that you will find. Okay. So, in this case, as we mentioned earlier in the IR based model, you also have the same retrieval as part of this. What additional thing that we have added is, we have added the question processing mechanism, where the type, the hierarchy and the fine grained types are found. So, from the documents we retrieve various passages, and then using the newly found feature set. So, using the newly found feature space, we should be in a position to extract answer which are better than IR based models. So, that is the idea here. Okay. So, again the document retriever, as I mentioned earlier, it could be a Solr, Elasticsearch or LSA that we had used earlier, and answer encoder could be based on the RNN. Let us look at one of the examples of how this could be achieved using neural nets. So, before getting on to that, let us find out what are a span. I think I mentioned about this, right. So, we already spoke about identifying this span of tokens for each questions, correct. So, for another question, the span of tokens are, what is the invention of C.V. Raman? Given a set of paragraphs, you find out the span of token that matches the question you have here. So, again the span of token starts from, let us say it is starting from Pi to Pi plus j. Okay. So, this is what we want to achieve. So, in this case there is one more thing that we are introducing. We need to find out what is the value of Pi, the starting span that is what I mentioned as Pi here, Pi plus j. So, this is something that we need to find out, not just the paragraph, but we need to find the span of text. So, how do we do that? So, for that again, if you want to use any models using a neural network, you definitely require a corpus. So, Stanford question answering data set provides you an interesting corpus, where it helps you in terms of finding out for a given paragraph what are all possible questions that you can come up with. So, they used humans to really codify the questions when they provided a lot of paragraphs from the Wikipedia. So, in this case, there is for a given paragraph, what are all the possible questions that you can expect for the given paragraphs. So, in this case I have taken the keyword steam engine and it provided a paragraph and then gave a set of questions, and the ground truth answers are also available as part of that. So, the question would be, along with geothermal and nuclear, what is a notable non-combustion heat source? Okay. The answer is available as part of this paragraph, and the ground truth answers are provided by the human. They form the question and also provide the answer for that. That is what is used as the ground truth answer. They also provide the span of text. So, where it starts and where it ends for each question. So, if you go to the website here, you search for Squad Stanford, you will get this link. You will be able to go and then browse through the Squad data set, which is really used for reading comprehension for the machine. It has 87,000 examples for training and 10,000 examples for development. All questions and answers are composed by humans through crowdsourcing, and then they also have provided this span of text for all the questions that could be answered. Okay. Having obtained additional feature vectors, now we should be able to do a better job, I guess, right, with respect to training the network, with respect to matching the question with the answers and so on. So, in this case I am not going to be doing the short text conversation model as we had done earlier. I am just skipping that part of the short text conversation model, getting into some portions of question answering, using what we had seen earlier, in terms of classifying the questions into various hierarchy and different types, and we can use the a part of speech, we can use chunks and so on. We can provide a better input to the system. We also have word vectors, assuming that we have good quality word vectors coming in from some of the word embedding models. We should be able to provide a good input to the question answering system. So, again, when you look at the question answering system, it is very similar to what we saw earlier in the conversational modeling, where there is a query and the query is related to the post and the response. In this case, we have a query question and we have a corresponding answer to that question. So, again in this case we should be using the information retrieval engine in order to get the documents, extract the paragraphs relevant to the question from the documents, and spot the span of text within the paragraph that we have retrieved, and then train the models as we had done earlier. So, we can do the training differently in this case. Here we train the question module separately, we train the answer module separately, but connect the two modules using the question encoding that we create. So, and that is what we are going to be looking at right now. The question encoding is a separate entity by itself, where we create the weighted sum of all the words in the question. Okay. So, we have 100,000 questions. I use an RNN to train the question module or question encoding. So, the idea is to find out if a similar question of that comes in after the training, we would retrieve an equivalent question encoding which we could use in the answer module. Okay. So, here we have the weighted sum of all the words is what we are going to be encoding. The word embedding for each word is fed. Every time state hidden QI is output. So, note the type of the notation here. So, this is the question word, QI is the question word. QI is the output from the hidden unit. Okay. For all the time states, a weighted sum q and a single embedding of the question is output. So, at the end of the hidden layer, this is what you get. Okay. And then every q vector is obtained using this relationship, okay, where Bj is nothing but the exponential of, rather the ratio of the exponential of the weight and the hidden value of the jth element to the sum of all of those. It is very similar to what we saw in the softmax side, right. So, this is a weighted sum of all the hidden values that you find from the hidden unit, and this is what we are going to be learning. Okay. So, in the same fashion, we have to have certain notation for the paragraph as well. We have the question with n tokens, and then we have capital P again. This is the encoded paragraphs of P hat, which contains m elements. What is that P hat? We will define now. So, we for every paragraph that we have retrieved, right, using the retrieval model, or if you are going to be using the squad, you have the paragraphs made available. We can find the embedding for each of the word in the paragraph. Okay. So, the small p I, pay attention to the notation here without any bold. So, you have a paragraph and every word is represented in that paragraph by this notation. P I can be matched exactly by one question word. Okay. Suppose if we have the word which is also available as part of the question, then we have one feature called F2, which is equal to 1. And then we can use the token features such as POS, NER, TF or TF IDF as another feature set. And then aligned question embedding is also captured. Okay. So, we also want to find out, along with the question that we have, we want to see how these words are aligned with the paragraph that we have found. So, you remember in the translation model, we try to find out the phrase alignments or word alignments. In the same fashion, we want to find out the alignments of the words that are available as part of the question as well as in the paragraph using this relationship. Okay. Here this could be a ReLU and so on. I think this is the first time we are looking at ReLU in the equation, correct. So, why do we do this? The idea of bringing in this is to find out if if in the question if we have car and then in the paragraph if we have vehicle, we should be able to match that. They shouldn't be considered as two different words. So, that is the reason why we want to bring in the soft alignment through this model. Okay. So, if you look at the QA system, I am not going to go into the details of this. Again, this is available as part of the research paper. I want you to go through the paper to understand this in detail. Okay. So, we have a question module and we have an answer module here, okay, and each can be independently trained. So, what is that we get from this? As we mentioned earlier, the question is who is C.V. Raman, and then for each word we have the embedding, and you know well in the RNN we through the time slice we input one word at a time, and then at the end we create a embedding for the question which is the weighted sum, and that is what we are going to be using it in the answer module as well. Okay. So, let me remove this now, and then in the answer module for the question that we have, who is C. V. Raman? C. V. Raman was an Indian physicist. Okay, so that is the answer, and this span is available as part of the paragraph. Okay. So, we are going to be feeding in the entire paragraph one word at a time, and then we are going to be trying to get the attention using this AJ model, okay, as mentioned in the previous slide. That would be input as part of the vector which is defined by this p hat I. So, here it is p I, each one is a, so this is, let me p I here, and then once you provide other features into this, it is transformed, the input is transformed into p I hat, and that is what we feed as input to the RNN. So, now we have a paragraph encoding available as part of that. We have the question encoding available that is coming in from there, and then using this we want to estimate the starting and the ending position of the span, and this is the goal of this. So, the goal of this is to train the model to find the start and end of the span. Okay. So, the goal is to predict the span of token that most likely the correct answer. RNN is trained using the paragraph vectors that is obtained using the p I hat to predict the span SP start and SP end. So, here the SP start and SP end can be found using this relationship here. And then finally, the SP start and the product of those two should be maximized to get the probable starting and ending position for that. The goal is to find the SP start and SP end, and then the prediction of the span of token is going to be found using the neural net model, and that would give you the most likely answer for the question. Okay. Okay. So, in the experiment what they have done is they have used 3-layer bidirectional LSTM with the hidden 128 hidden units for both paragraph and question encoding. They used a Stanford Core NLP toolkit for tokenization, generating lemma, part of speech, and so on. Okay. And then at the end what also they have done is they try to find out a score, FN score, okay, which is used as the benchmark to find out how good that model is. Okay. So, with all the features, using all the features that I have mentioned earlier, the F1 score is about 78.8, and then this should be F token. In the same fashion it is and then here it is F then the last one is So, remember we spoke about those features as input to the system. If you look at this answer part of the RNN. So, we have a part of speech that we are feeding in. So, for example, in this case ramen is being fed. So, it is a noun form and then it is available as part of the question. So, we have this one here and then the type is person, that is what we are feeding in. So, all the combinations of those feature vectors are formed here rather than just feeding only the embedding. So, we have a new combination of the feature vector and that is what is being fed, okay. And that is what we are talking about in this case. So, when you use all the feature vectors, the F1 score is about 78.8. When you use all the features, the F1 score is 78.8. When you do not use F token, the score is 78. There is not much of change. Okay. When you do not use F token feature, there is not much of a change. When you do not use exact match, see the reduction in the FN score. So, when the score is high, that means we have a good system. Okay. When you do not use the aligned, again it is similar to what you find when you did not use F exact match, but when you discarded these two features, the system performs poorly. That means, this feature is very important for identifying the span of tokens. So, that is what this experiment says. FN score is obtained using this relationship. So, this is a very important relationship in the information retrieval, and if the beta is equal to 1 or alpha equal to half, what we get is the FN score. FN score, when the beta is equal to 1, it gives a balance measure where the precision recall are given equal weights. So, when beta is equal to 1, it is a balanced measure that gives equal weights to precision and recall. Okay, and this is the formula you get when you have beta equal to 1. This is part of the information retrieval and do not want to get into the details of all of these. And then what is P here? P is nothing but the precision. Precision is given by the ratio of the number of relevant items to the total number of retrieved items, and recall is the number of relevant items retrieved to the total number of relevant items. So, you can also draw this in this table as given here. So, you have true positives, false negatives, false positive and true negatives. As it is part of the precision, if you have the ratio of the true positive to the sum of the true positive plus F positive, then the score, what we score is the precision. And then for the retrieval or for the recall, the ratio of the true positive to the sum of the true false negative, and this is what we use as part of the evaluation of the conversation model. Okay. So, with this I conclude this. I urge you to go through this paper to understand the concept very well.